Good morning, friends, and welcome to the session of the fifth and last day, the first session of fifth and last day. And in this session, we have Dr. Snehal Mevada with us. Sir is working as an assistant professor in Department of Civil Engineering, Birla Vishwakarma Mahavidyalay, Vallabh Vidyanagar. Sir has the teaching experience of around 18 years. Sir has completed his graduation and master degree from BVM itself, Sardar Patel University, Vallabh Vidyanagar in 2000 and 2004 respectively. Sir has completed his PhD in structural engineering in seismic response control of asymmetric buildings from IIT Bombay in 2012. The area of interest of Snehal sir is in earthquake engineering, structural dynamics, and structural control systems. Sir has published many research papers in reputed national as well as international journals and conferences. So at this juncture, I welcome Dr. Snehal Mevada on behalf of Marwadi Education Foundation and Atal Academy AICT for sparing his valuable time in this knowledge sharing platform. So I invite Dr. Snehal Mevada to deliver his session on structural control systems. Welcome, sir, and I hand over the session to you, sir.
Thank you, sir. First of all, I would like to thank the management of Marwadi Institution and Civil Engineering Department of Marwadi uh, Institute, Dr. Tarak Vora and the team for inviting me for to share the knowledge with all of you. I hope my screen is visible.
Yes, sir. Yes, screen is visible.
Okay. So good morning to all participants. Today I came to know that today is the last day of your this faculty development program. So we are going to discuss about the structural control system. So mainly we will include these some few contents in context to our topic. First of all, we will see some of the photographs which normally I show to the audience just to get the feel of the uh, content, and it creates basically the need for the study. Then we'll see the objectives of structural control, then little concept of resonance, need for dynamic analysis, need for structural control. Then we'll briefly see the types of the structural control system, and we'll see the application of damper and few case studies. So just few of the slide I will show you. Just they are the photographs from our unfortunate event of the 2001 Bhuj earthquake. So just I'm scrolling the all the photographs around 10 or 12. So this will just give you the highlight of course you must have seen all these photographs in your many previous speaker or in your study also. This is just creating a interest in the subject, basically that subject in the sense interest in the sense it emphasize the importance of earthquake engineering in the society actually. That you just see the photographs, failure, collapse. So we can imagine what earthquake can do if the structures are not properly designed and constructed. See, people are spending their whole life to earn the money and to build a one house, and what earthquake can do just in a few minutes. Okay, so these are the just few photographs. Now again, you must have seen this particular slide. This I have taken from earthquake tips. Uh, just these numbers will give you the idea that how much continuous disturbance is going on underneath the earth. Actually, if you talk about the magnitude 1 or 2, minor or micro, we can say micro earthquake, they are occurring per day around 8,000. This is world average number. Very minor earthquake, they are coming 1,000 earthquakes per day. Those have the magnitude 2 to 3. 3 to 3.9 minor earthquake, we say 49,000 earthquakes coming yearly, and so on. If you consider year once in a year, one earthquake comes which is of magnitude 8 or greater than. So you can see a continuous 365 days disturbance due to the earthquake. And if we do not care about the proper design, detailing, workmanship, material quality, everything, all planning, execution, configuration, if any of the component missing, then it will lead to catastrophic or the disaster which we have seen in the earlier photographs. Now two words are there. One is analysis and design, very basic words. uh, which can be defined by means of these three parameters: force, system, and response. It means if we know the force, if we know the system, and if we want to calculate the response, that procedure is called as the analysis. And on the other side, if we know the force, if we know the response, means let's response means we want to have some zero deflection, let us say, if we consider about the beam. So if we know the response, so based on that force, to obtain that response, what should be the system design. Now here, when we talk about the earthquake engineering, this analysis word becomes the seismic analysis, and design becomes the seismic design. For mainly the analysis, we are having IS 1893, which deals with the earthquake forces and how to estimate the earthquake forces basically. So it covers the seismic analysis part. The seismic design, if we talk about, it is basically the uh, ductile designing, that is as per IS 13920. Seismic design philosophy, I'm sure, definitely sure, that this must have been covered by the earlier speaker, and this is a very basic thing. So as all you are attending this earthquake engineering STTP FDP, so you must have the background of earthquake engineering, and you must have seen this, that as per IS 1893, basically we are not designing or we are not focusing on the earthquake proof structures, but we are mainly considering the earthquake resistant philosophy, that is the seismic design philosophy. That under minor shaking, there should not be any failure to the structural component. There may be some minor damage to the non-structural component. In the second category, in the moderate shaking, there may be some repairable damage to the structural component, and there may be irreparable damage to the non-structural component. And during strong shaking, there may be some irreparable damage to the structural component, but the main philosophy of main philosophy of our code is that the building should not collapse. That is the main thing. There should not be human loss actually. If even if it is a collapse, even if it is a failure, it should be a ductile failure. So based on this, we are dealing all these particular clauses. uh, as I mentioned, many parameters are there, just like as these are the four important virtues which uh, are there for the any good earthquake resistant building. The building should have good structural configuration, it should have adequate lateral strength, it should have adequate stiffness and good ductility. If we care about all these thing, then we can make sure the building will be earthquake resistant. Now configuration is equally important as stiffness and ductility. So there is one famous quote by Henry Jacob, who is a famous earthquake engineering of USA. What he said is, if we have a poor configuration to start with, all the engineer can do is to provide a band-aid, and basically it improves the poor solution as best as he can. And on the other side, if we start off with a good configuration and a reasonable flaving system, even a poor engineer cannot harm its ultimate performance too much. So this is emphasizing how much importance is there for the configuration actually. Again, the four points which we can consider: proper planning, proper structural design, good construction, and the regular maintenance. Now, basically, whenever we are dealing with the structural control system, the mainly which the main analysis which we have to do, it is basically the dynamic analysis. Now, what is the need for the dynamic analysis? Uh, as per IS 1893 code, there are mainly two type of the analysis: static analysis and dynamic analysis, right? In static analysis, that is seismic coefficient method, as per code. Dynamic analysis consists of two methods: time history method and response spectrum. These are the broad analysis type, right? I have not included in detail about the linear, non-linear analysis, etc. In both the category, linear and non-linear analysis are there. uh, but it has been covered by the previous speakers, so I have not included. Now, what is the need for the dynamic analysis is, let's say we have the structure. We are calculating the base shear as per the code equation VB, you must be aware of. And we are calculating that design horizontal seismic coefficient AH, right, which is consisting of mainly the four parameters: Z, I, R, and SA by G. SA by G is based on the time period. Now, if we consider the static analysis, then we have just a sample equation I have written. Number of equations are there for the different type of the building, with shear wall, without shear wall, etc. But just to give you the basic idea, one of the equation, conventional equation, which is most commonly used, it is 0.09 h by root d. That is the equation. Now, let us say if we have this structure of G plus 2 story, let us say M1, M2, M3, 3 mass and 3 stiffness. This building, this elevation, vertical elevation, it has these two plan, let us say two different cases. In case one, all columns are of size, let us say 300 by 300. In case two, all columns are of, let us say 600 by 600, right? Height is same, plan dimension is same. So if the height and plan dimensions are same, plan dimension of the building are same, then the time period which we are calculating, it will be same for both the building. But actually, if you imagine, just imagine it is a model structure and we are putting it on a shake table. If you put these two buildings on the shake table, then obviously there will be a different behavior, because the stiffness is different, column sizes are different. But that effect, that behavior will not be captured by this time period, which is based on the our empirical formula, right? That is the static seismic coefficient method. And hence there is a need to perform the dynamic analysis to actually capture the real behavior of the structure based on its stiffness and mass proportionality. And hence we are going for the dynamic analysis, and we are calculating the time period using the conventional equation 2 pi by omega n, where omega n, that is the natural frequency, which will be based on square root of k upon m, right? This is just the basic equation I am highlighting, because this is not our topic of discussion for today, but just I'm emphasizing the need for the dynamic time history analysis, which we need for the structural control also. uh, this is the equation to calculate the natural frequency. It is basically the for the single degree of freedom system, right? If it is a multi degree of freedom system, then we have to perform the modal analysis, eigen analysis, etc. Now let us go to the seismic vibration control of this structure, that is called as the structural control system. So the main objective of our civil engineering, as we know, that it is the mainly to design and construct the safe and stable structures which can resist the static as well as the dynamic loading, right? Static meaning conventionally, let us say the gravity load, dead load, live load. Dynamic loading comes considered, it includes the, let us say, the wind and earthquake, which are our conventional dynamic loading. Now, this can be achieved. The objective of this civil engineering structure, it can be achieved by traditional approach, which we are using currently. That is designing the structure as far as with reference to the strength as well as the ductility aspect, but sometimes it may not give the guarantee for the safety of the building against the dynamic loading, which is very random, very irregular in nature actually, and highly uncertain. Sometimes what happens, if we have, let us say, tall structure, let's say if we have a 100-story building, just consider, imagine if we have a 100-story building, and in comparison to that, just imagine if you have a 3-story building. If we have a 3-story building, to control the displacement of 3-story, what should be the size of the column? Just randomly, let us say it is 450 by 450 mm. Typically our flat or apartment, 450 by 450 columns which we are providing for 3-story building. Now in the same proportional, rough guess, in the same proportion, if 450 by 450 mm is the size of the column required for 3-story building, then what should be the size of the column required for the 100-story building, to control the displacement, to control the drift, to control the acceleration, to control the deflection? You can imagine the column size will be of room size, almost room size, right? So it may not be a feasible solution. So to control this tall structure, we need to provide some, we need to include some modern approach which consists of the structural control. So the modern approach, basically it includes, to achieve the safety, is to control the response of a structure which is inducing due to the dynamic loading, and this can be achieved by using various structural control methods, which we are going to discuss in detail today. So based on this particular need, few objectives are there for the structural control system. Structural control system, uh, main objectives are to secure the life safety, that is obviously the number one, that is our main need. To upgrade the comfortability for the user, uh, in the sense, again, just let us go back to that previous example, 100-story structure. uh, During the wind, let us say, during the wind, if the wind is blowing, during the wind, if there is a 5, let us say 1 centimeter displacement in the 100th story, then what will be the comfort level of that user, right? It will not be a functional actually. So comfortability of the users is equally important in comparison to the, to maintain the building function. Obviously during the earthquake, whenever there is a some collapse or failure or damage, then the building should be, immediately it should be in a functional mode. And to secure the safety of the non-structural element, if we have, let us say, some very important structures like a hospital, a nuclear power plant, right? Then for these type of structures, non structural elements are equally important. Like let's say if we have a hospital of 3-story, and at the 3rd story there is operation theater which is having some very costly equipment. If we have a nuclear power plant where pipelines are going on, so to save the to make sure the safety of the non structural component is also equally important. That is also the main objective of the structural component in addition to the structural element. So the dampers which we are going to, the control which we are going to use, it is just like as the shock absorber, which we have seen, and which we have in our vehicles. So in a vehicle, you must have seen, in the front wheel there is a piston and cylinder, in the rear wheel there is a piston and cylinder surrounded by the spring, right? They are called as the shock absorber in terms of the automobile industry. If we talk about our structural or the civil engineering industry, then basically we call it as a damper. Exactly the same mechanism, exactly the same configuration. uh, we are putting the damper, let us say this is the structure, the damper we are putting like this, right, inclined. This is just a broad figure. So the dampers, they are just like as a shock absorber which we have in our vehicle, and it can absorb the jerk, right? Just imagine you are riding this bike without this shock absorber. If there is some unevenness in the road, right, then it will be, immediately it will be affected at the seat level in terms of the jerk, right? Just imagine your ride, the comfort level which you are having without the shock absorber. And now if you put the shock absorber, and just imagine that you are riding this particular vehicle in some rough or uneven road, even those jerk will not be transferred to the seat level actually, because in between there are shock absorbers which will absorb the particular energy. So the seismic energy is transmitted through them means through the absorber, and dampers absorb the part of it, and thus the damp the motion of the building. It reduces the basically the vibration of the structure. So mainly three types of the vibration which can be controlled by the any of the structural control system. Small vibrations we can control, obviously. Micro tremor, traffic vibration, and vibration caused by the machine. It can be easily controlled with the help of structural control system. uh, Wind vibration, usual wind or a strong wind, that can also be controlled easily through the structural control system. And of course the seismic vibration, which is of the main concern, that is the small, medium, or the strong earthquake shaking. Whenever the shaking comes, the structure should not have the displacement, acceleration, severe displacement or severe acceleration, so we can control it. uh, just 2 3 slide we'll see the application of the damper, some photographs of the real structure, and then we'll go to the type of the system, and then again we'll see in detail about the this real application. So these are the different type of the dampers. This is just the first left hand side figure. It is the viscous damper, which it is exactly the same as the shock absorber in our vehicle. Then we can have the another type of the damper, that is a friction damper. Then we have the metallic damper. These are the different configuration in terms of the incline bracing, in terms of the cross bracing, in terms of this horizontal arrangement. So these are the type of the damper. These are the ways by means of which we can provide the dampers in the structure to control the any of the response, let's say displacement, velocity, acceleration. And ultimately by controlling the displacement, velocity, acceleration, we can control the base shear, base torque, etc. A few photographs just to give you the idea how the dampers are fitted actually in the structure, real structures. These in this figure you can see this bracing, these are the dampers, this yellow color. So this is the way how to fix the damper in the actual structure. These are the dampers again. This is the deck of the bridge where this damper is there. This again some structure where these dampers are fitted. This is the bracing and the dampers are fitted, right? So this is the way how to use the damper. Now the main fundamental principles of the structural control system. The main principle is basically it is transferring the vibration energy from the main structure to the auxiliary system. Just imagine our means recall our that vehicle example. What the shock absorbers will do, they will transfer the energy, means it will they absorb the energy, whichever is the energy, whichever is the based on the jerk due to the unevenness or the roughness of the road, right? It will be absorbed by that. So to transfer the vibration energy from the main system to the auxiliary system, to reduce the flow of input excitation to the main system, means in between, means between road and seat level there are shock absorber. So in between the shock absorber will absorb the energy. uh, to subject the structure the additional damping, means by whenever we are providing some structural control system like base isolation or primarily the damper, basically we are increasing the damping to prevent the building from exhibiting a resonance. You must have heard this in many of the uh, starting from our school level physics, that the resonance is a very dangerous phenomena. That whenever there is a resonance, then we have to control actually. So this can be very easily controlled by means of providing various structural control systems. And to provide a structural system with a computer controllable forces, so these are some fundamental principles requirement for the structural control system. Now what is the required item for the structural control system itself? So any of the structural control system, it should be a fail safe mechanism, means it should not do something wrong to the structure actually. To be back at the original position, right? Of course it is the need actually, where building should be back at the original position when the big wind or earthquake comes or ends. Hysteresis damping mechanism sometimes prevent building going back to the original position. So we have to take care that the structure should come immediately to the original position. Means the structural control system should be such that it will bring the structure into its original position. It should have obviously the good aging property for the number of years actually, and it should have no that is the ideal situation that it should have the no or less maintenance. So these are the required items for the structural control system. Now the resonance just now which we have seen, you must have seen obviously this equation of motion, that is mass into acceleration plus damping into velocity plus stiffness into displacement, and on the right hand side we have mass into ground acceleration. So this is called as the equation of motion. We have the natural frequency, square root of k upon m for single story building, or we can say the single degree of freedom system. If it is excited by the forcing frequency, and you know where when it is forcing frequency, when it is matching with the natural frequency, the resonance occurs. So with the help of the structural control system we can avoid the resonance also. If we have all the building omega n 1 2 3 4, let's say we have 4 building, if earthquake have the frequency omega, then whichever frequency matches with this forcing frequency, that building will excite. There is one famous example of the wind induced vibration, wind induced resonance actually. You must have heard this. It is a Tacoma narrow bridge. 1st July 1940 was the opening date, and it collapsed on 7th November, just immediately in a few months. That is because of the wind induced resonance. This is the newly constructed bridge. Similarly, one famous example of the resonance is the Mexico City earthquake. On 19th September 1985, there was a main shock of magnitude 8. Sorry. 1985, there was a main earthquake. On the next day, there was aftershock. On the main shock, on the 19th September, hardly there was damage to any of the structure. But what happened on the next day? On the next day, even though magnitude was less, obviously, which is the aftershock, almost 1100 building suffered damage actually. 400 building collapsed and 700 building heavily damaged. Later on they made some survey analysis, and they found that all these 1100 building were in the range of 6 to 14 story actually, and they were having the time period of 2.5 second, which matches with the forcing frequency. So these are the cases of the resonance. Now as we have seen, four types of these control systems are there primarily: passive control system, active control system, hybrid control system, and semi-active control system, which is the most recent system which is using worldwide. So one by one we will see all the type of the control system including the example and application, and then we'll go to the case studies. So as we have seen earlier, this is the equation of motion of the structure without any control mechanism, means without damper or without isolator, base isolation. So the equation of motion will be this: mu double dot plus cu dot plus ku is equal to m into ug double dot. This equation of the motion, if you solve based on the numerical method, that is called as the time history analysis. If we solve it, we'll get the displacement, velocity, and acceleration of the structure. Now in the building, if we put the control, means if we put the damper or isolator, then one additional component will come over here, that is FD. FD is the force due to damper or the force due to isolator, let us say. So that component will be additionally coming over here, and it will absorb the energy, and it will help the system to reduce the displacement, velocity, acceleration, and based on that further properties. Without control and with control, just a picture showing this red color is the showing, let us say, the displacement versus time for any of the structure which is without control. And if you put some control, means these are just the representative figures. If you put some control, actual case study we'll see. If we put some control by means of isolator or damper, then the response can be reduced like this. The response can be reduced. See, the black line indicates the displacement, maximum displacement. Here drastically there is a reduction in the displacement or any of the parameter, right? You see this red dotted line indicates the structure response without damper or without isolator, and the black color indicates the with isolator or with damper. So we can say there is a significant reduction. Now basically what this is doing actually, this is just the code from the UBC. Similar we have in our IS 1893 also. In our IS 1893, two different graphs are provided like this: SA by G versus time period. One is for the seismic coefficient method and one is for the response spectrum method. Now just this I have put just a sample, just to give you the feel, or just to understand the importance of the damping actually. If we have, let us say, the 5% damping, which is the conventional damping as per our IS code also, IS 1893, the damping which we have to consider, it is 5%, right? Irrespective of the material that has been included in the revised current version. In earlier version, based on the material, the different damping was there, like 5% for RCC, 2% for steel, but now somehow it has been merged to single value. But let us say we have this SA by G, structural acceleration, spectral acceleration, versus the time period of the structure, which we are calculating either by the dynamic analysis using the equation 2 pi by omega n, or using that empirical formulas like 0.09 h by root d. Now you just, this graph is just highlighting when we increase the damping, 5% is the damping, right? When we increase the damping from 5 to 10, 10 to 15, 15 to 20, with the increasing damping the acceleration is reduced, right? So just a basic idea that what is VB, base shear, which we are calculating. Ultimately we are using base shear to calculate the design lateral force, Q, right? Q is the notation as per our code. So to calculate design lateral force, we need base shear, and base shear is directly proportional to the acceleration, that is SA by G. It is basically F is equal to MA with some coefficient Z, I, and R. So if we increase the damping, SA by G will reduce, means the base shear will reduce. When the base shear will reduce, lateral forces will reduce. So the structure is subjected to less forces. So that is the effect of the damping. Now the passive control system, first if we look at in detail, this is the figure number first, is basically the conventional system. This is the block diagram, or we can say the flow chart of the structural control system. If we have a structure which is getting excited by the wind or earthquake, let us say, then it will give us the response, means as it is our conventional building structure is there, it is subjected to a wind or seismic vibration excitation, and it is displacing or it is deforming, it is vibrating, oscillating. Passive control system, in passive control system what we are doing is, in the structure, along with the structure, some device is there, we call it as a PED, that is passive energy dissipation device. So it is just like as a, this conventional system means it is a vehicle or the bike without shock absorber, and passive control system means a vehicle with shock absorber, just like as that, right? So depending on its property, that piston, cylinder, spring, fluid, depending on its property, it will absorb the energy. And obviously you can have the idea that whenever there is excitation in comparison to this conventional system, the excitation will be absorbed by the PED, passive device, and the response will be less, right? If there are means conventional system, let us say the displacement is 10 centimeter. Here some of the displacement means some of the energy, excitation energy will be absorbed by this, and the displacement instead of 10 centimeter it may be 5 centimeter, just broadly I'm saying. So it will give the less response. Actually the displacement and acceleration will be less in general, right? Of course it depends on the type of the structure, type of the damper actually. So it is just like as this conventional system means structure as it is, which is subjected to earthquake force, ground acceleration, and shaking. And on the right hand side we have the building with which is equipped with PED, passive energy dissipation device. A passive system means it will not change from time to time or in real time. That's why it is known as the passive. So in the passive system basically, it doesn't require any power supply. That is the biggest advantage we can say, right? It is usually relatively very inexpensive. It consumes no extra energy, right? That shock absorber which we have in our vehicle, right, piston, cylinder, spring, doesn't require any external supply or the battery backup. So it consumes no extra energy, no electricity. It is very stable, and it works even during a major earthquake. That is the advantage. These are the advantage of the passive control system. Disadvantage, the biggest disadvantage of the passive control system is that it doesn't make any real time changes to the system. Real time in the sense, just recall again, go back to our original example. We have the vehicle equipped with that piston, cylinder, shock absorber, right? If some minor unevenness is there in the road, right, it it can be absorbed by those shock absorber. But there is some major unevenness is there. Let us say very heavy jerks are experienced by the vehicle or by the due to the road, right? Then we will not have the comfort at the for the while we are riding the vehicle actually. Because the passive system, the shock absorber which are equipped in that particular vehicle, they are having their own property. Their size is fixed, diameter is fixed, piston is fixed, viscous fluid is fixed, spring is fixed, everything is fixed actually. So it is giving us the response, it is giving us the response, it is absorbing the energy depending on its fixed property, fixed set of parameters which we cannot change, right? Parallel to unevenness in the road, we cannot change the property immediately, right? So that is the disadvantage, that passive control system does not make any real time changes in the system. These are the few types of the control passive control system. Basically mainly it consists of two category: isolator and damper. So base isolation system and energy dissipation system. Base isolation system, we have all these pure friction base isolation, then LRB, FPS, then elastomeric bearing, right? You must have heard these in earlier speakers in detail. Energy dissipation system, we call it as a damper. They are also of passive control category. We have the different types of the damper: passive friction damper, passive viscoelastic damper, passive viscous damper, yielding metallic damper, tune mass damper, tune liquid damper. These are few of the dampers. The shock absorber which we have in the front vehicle, in the front wheel of the vehicle, they are known as the viscous damper. And the shock absorber which we have on the rear wheel, which is having the piston cylinder surrounded by the spring, that is called as the viscoelastic damper in terms of the our language. uh, uh, this probably I think must have been covered by the previous in the first day, that base isolation, whenever we are providing the isolator, it basically elongates the time period. Actually the time period of the structure increases. So this is our just like as SA by G versus T graph just now which we have seen. So SA by G versus time period graph which we have, right? And if a fixed base structure, if the fixed base structure is having this time period, when we provide the damper, when we provide the isolator, the time period increases. Time period increases means SA by G reduces. Whenever the SA by G reduces, the base shear and design lateral force will reduce. This just showing the effect of the isolator. One left hand side building is without isolator, right hand side is with isolator. So in between substructure and superstructure, whenever we are putting the isolator, the energy will be absorbed. uh, a typical example, our Bhuj hospital. This is the first actual building of our country. This hospital was, you must be knowing that it collapsed during the 2001 earthquake. And it is having the basement plus G+2 structure story. So this hospital building is equipped with the isolator. I'll skip this part actually, must have been covered. uh, Bearing, lead rubber bearing, sliding bearing, elastomeric bearing, these are the few of the photographs showing the isolator which can be placed actually. Now let us go to the active control system. That is the second category. Active control system, basically what happens, this is the structure. Earlier, with reference to our earlier block diagram, this is the excitation. So excitation is measured by the sensor, right? uh, Through the accelerometer, let us say. The structure is giving us the response, so that response is also measured by the sensor. The response of the structure, excitation of the ground, both will go to the computer controller, right? That controller will give some command to the actuator. Actuator will decide how much the force to be applied to the structure so that it can be controlled. So two sub mechanisms are there. One is the open loop, another is the closed loop, feed forward and back feedback control. So basically what is happening over here is, let us just roughly, I'm giving you the idea. If you have a structure, if it is displacing 5 centimeter on the right hand side, just imagine if you have a single story building which is getting displaced by 5 centimeter on the right hand side, then what should be done? That we need to bring back that system into its equilibrium position. So there should be some force, pull force, let us say, just in a simple language. That there should be some system, there should be some actuator. So actuator should apply the force to the structure so that it comes to zero displacement or equilibrium position instead of that 5 centimeter. So that 5 centimeter, that is a displacement which is, that is a response here which is measured. That measurement of the 5 centimeter will go to the controller. That controller, computer controller, will give some command to the actuator, and actuator will generate the force so that the structure will come back to its original position, right? That is the active control system. Basically it has all these three devices, these parameters: sensor, control devices, and the actuators. So these actual active control system, there are some advantages parallel to the in addition to the disadvantages. That the advantage is, it has the very high effectiveness in the response control, relatively insensitive to the site condition and the ground motion. Any type of the random ground motion can be controlled by means of the active control mechanism. Equally applicable to the wind or earthquake, right? And it is a very robust under the uncertainty in the very wide range of the dynamic loading actually. So obviously it is the good system, it was good system. But parallel to that, the biggest disadvantage of the active control system, if we do not touch the cost aspect, then it is the large power source. It requires a very large power source actually. um, just imagine what should be the capacity of the actuator which we need if we want to control, or if we want to control the single story or 5 story or 10 story or 20 story building actually. You can imagine what should be the size of the actuator, capacity of the actuator. And we need the full computer control system. So, but what will happen, that whenever the earthquake comes, normally there may be some failure or the collapse or damage to the power station itself, right? Distribution system, right? Electricity failure. So that even if you have a very advanced active control system, but if there is a earthquake, right, during the earthquake there may not be electricity, right? Due to that, what happens that the whole system, even if it is properly managed and maintained, but it will not be of any use if there is no electricity, because it requires a very huge power source actually. That is the biggest disadvantage. So it was developed and equipped obviously in many of the mid-rise to the tall high-rise structures in worldwide, but it has these disadvantage actually. These are the little means few types of the active control system: active mass damper, then we have the active tune mass damper, active tune liquid damper, column damper, active variable stiffness damper. We'll see just some of the few videos also I downloaded through internet, YouTube. Hybrid control system. Hybrid control system is just a mixture of passive and active, as the name suggests actually. So we have these both. In passive we were having this, in active we were having this, in hybrid we are having both. So what is happening, both systems are there, passive is also there, active is also there. So whenever there is a power supply, whenever there is a failure of the power supply, right, the active will not work, but the passive component will be of use actually. So that is the that part, that in the case of the power supply, the passive component of the control system still offers some degree of protection, but so it is obviously parallel to that, it is difficult to control the multiple devices, quite complicated design and it implementation, and obviously the cost aspect will be also that we have to mm, spend more, right, to include the passive as well as the active. Hybrid mass damper, hybrid base isolation means that in addition to the damper, isolators are also provided. So nowadays, very recent control system which are being used worldwide, it is the semi-active control system. It is a very recent one. So the semi-active control system, it basically, you just image just see what is the difference between the active flow chart, active control system and the semi-active control system. In active control system, the actuator were connected to the structure. Actuator or computer controller means computer controller through actuator was connected to the structure earlier, whereas here computer controller or actuator is not connected directly to the structure, it is connected to the passive device itself. So what does it mean, that structure, the purpose of the computer controller or actuator is not to give any command or not to give any supply to the structure, but it is making some real time changes in the passive device itself. Just I'm coming to that point. Let us say this is a passive damper, right? Now passive damper means it is just like as our shock absorber of front wheel of the vehicle. Agreed? See, this is the our cylinder, then we have this two chamber and this is the piston, right? So when you push the cylinder, when you push the piston, the fluid, viscous fluid, which is in the chamber number 1, it will transfer to the chamber number 2 through the orifice. That is a passive damper. That is the simplest mechanism of the our shock absorber or the passive damper. So now in semi-active, what has been done in the semi-active is, in the semi-active, people have modified this passive damper, viscous damper, just a little modification. What is the modification? The fluid will not transfer from here to here directly through the orifice which are provided inbuilt, but there is some additional way is created here, some additional path has been created. So if we create the additional path, now the fluid will not transfer from here to here directly, it will transfer via this path. So what happens, in between there is some control valve. Now obviously you can have the idea that if you open the valve fully or partially, or if you close the valve, then there will be a change in the velocity of the fluid. So depending on that, depending on the position of the control valve, the fluid velocity will be different, and hence ultimately the force offered by the damper will be different. Got it? That is the semi-active damper. So on what the controller or what this system has to do, this response measured by the sensor, computer controller. Now what the computer controller has to do, just it has to decide that what should be the position of the control valve based on the need actually. Based on the need meaning, if the displacement is of 5 centimeter, let us say, if the displacement is 5 centimeter, now what should be the force which should be applied by the passive damper so that it can absorb the energy which is generated through the 5 centimeter displacement. So when you provide the additional valve over here, computer control, computer meaning that there are some number of control algorithms based associated with the different type of the dampers. So different control algorithms, the mathematical control algorithms are there, programming. So that program, based on the input, based on the feedback received from the sensor, those programs or those algorithm, we can say, those algorithm will decide that what should be the position of the control valve. So here, what is the, where is the need for the power supply? The power supply is required just to control the valve only. It has nothing to do with the actuator, it has nothing to do with the total force which is required to be applied to the structure actually. So even if there is a power supply failure during the earthquake, these semi-active dampers will work very well, because just to open or close the valve, or to partially open or partially close the valve, we need to operate only the control valve. And this control valve can be operated with the help of some small vehicle battery also, right? So there is no need of the external power supply. Inbuilt battery backup will also uh, control the whole structure actually. So that is the semi-active damper. So these are the dampers as I mentioned. This is the damper, and this is again some of the photograph. So many so just I which highlighted the advantages, right? It offers the reliability of the passive device and maintain the adaptability. uh, very, as you can say, the large force can be generated with the small energy supply. Maintenance is also easy, right? Which is very highly reliable, uh, this one control system. These are the few type, means the varieties which we were having in the passive control system. The same, all varieties are available, all dampers are actually available, and they are placed physically also. uh, Semi-active viscous damper, semi-active controllable fluid damper. In controllable fluid damper, two sub varieties are there: MR damper and ER damper, that is magnetorheological and electrorheological damper. Then semi-active friction damper, semi-active stiffness damper, semi-active tune mass damper, and tune liquid damper. These are the different type of the dampers. So just we'll see one by one all these few photographs and the functional mechanism of all these damper. But before that, just let us see some of the few videos I have downloaded, just to give you the. I hope this video is visible. See, this is the shake table on which two models are there, experimental model. This left hand side is without damper, right hand side is equipped with the damper. So the dampers are placed like this. So you can see the roof displacement or the interstory drift actually. See. See the roof displacement or the interstory drift. See, immediately this building is getting controlled by means of the damper, whereas still there is some disturbance in this structure. So that is the effect of damping. Another is, as I mentioned, this is the structure, experimental again, without control, means this building doesn't have any damper. This is having passive control system, and this is having semi-active control system. You can see parallel to this video, there is one graph over here which will be created through the experimental setup. uh, the blue this yellow line is without control, passive control is the blue line, and semi active is the red one. So just see parallel to the video. See these three lines. This is the response measured by the sensor. Just see, yellow means without control, without damper. Blue means if we provide the passive damper, then this will be the reduction, and if we provide semi active, then drastic or the significant reduction will be there. Just see. See, it is showing the very effectiveness. See, that structure without control is still vibrating, whereas the vibration in the passive and semi-active stopped with the very significant effectiveness in the semi-active control system in comparison to the passive control system. Just see all these three pattern, right? Very effective semi-active control system. Some of the dampers which we have, which you must have seen, one of that is the tune liquid column damper. Means tune liquid column damper means, just see over here, this is a structure without damper, this is a structure with water tank. So water tanks which are placed on the roof or the terrace level of a tall structure, let's say 10-story high rise structure, 10-story, 20-story, or tall structure, maybe having the height of, you can say, greater than 200-meter. So the water tanks which are there, there are partitions. The partitions we have to make in the water tank, and those partitions, whenever we are making, the water will transfer from one chamber to another chamber, and it will absorb the energy. So it is just like as a sloshing effect. The energy is dissipated through the sloshing. Just see one more time. See the displacement, how it is getting controlled by tune liquid column damper in comparison to this left hand side, no control. See there is a sloshing, and immediately it is getting controlled, whereas this is still vibrating, right? So this is called as the tune liquid column damper. So that is called as TLCD. Another we have, that is a tune mass damper. This tune mass damper means the mass is placed at the roof, again at the terrace level. Here the mass has been placed. This mass is tuned to the fundamental frequency, and hence the energy can be, see the difference. This building is vibrating, this is also the vibrating, right? This is not tuned to the vibration. This is tune mass damper. Let us see one more time. See, this structure is vibrating, this is not vibrating. The energy is absorbed by this tune mass damper. See, it is immediately getting controlled, and the real tune mass damper has been placed. One very famous example, you must have seen the video. It is type A tune mass damper, where heavy ball, just like as a pendulum, is placed. This is the pendulum, this is the whole heavy ball, which is there, and which is tuned to the fundamental frequency, and with the help of that, see, it will vibrate like this. Whenever the building, means in short, whenever the building will move on the right hand side, this ball will move on the opposite side, and it will bring the system into the original position. So these are the ways by means of which the systems are provided with the different kind of the dampers. So semi-active viscous dampers, just like now we have seen, there was one path. Instead of that, multiple path can also be created based on the need. right? Number of multiple paths like this, see, right? So the fluid can pass parallel through the multiple route just to bring the required force. As I mentioned, semi-active controllable fluid damper. It have two category: ER fluid, electrorheological fluid, and magnetorheological fluid. Magnetic flux is being generated, with the help of which the force can be generated. This is the actual image of 20-ton MR damper, which is most commonly used and most successful semi-active damper. It is a semi-active MR damper, magnetorheological fluid. It is made by this Lord company. This is the actual damper having the capacity of 20-ton. Similarly, semi-active friction dampers are also there. Means now each and every damper which we have seen, each and every dampers have their algorithm, their mathematical model and the algorithm. So we have to perform some numerical study, experimental study, and then it is to be fitted to the structures actually. Similarly, semi-active stiffness dampers are also there, which can provide some additional stiffness to the structure to control the displacement. Uh, these are the same things which I have covered. Now let us see few photographs just to give you the idea that how the dampers are fitted in the real structures. So just I'm scrolling these photographs. These are the structures which are equipped. This was the structure just now which we have seen the video, type I 101 tune mass damper. This video we have seen this part. It is this building, this roof, this one. This is a tune liquid column damper which we have seen at the terrace. There is the water tank is there, different partitions are there, right? The fluid will transfer from one chamber to another chamber, and the motion can be controlled. These are the viscous damper. See, this is the bracing, these are the dampers. This is also the metallic, or the we can say the yielding damper. This is again a real structure which is equipped with semi-active hydraulic damper. This is the semi-active hydraulic damper. Number of dampers are placed. See here. In each and every story, they have provided the damper like this, in terms of the bracing. This is again a structure. This is the building equipped with this type of damper, semi-active hydraulic damper, again made by the Kajima Corporation. This is the some hotel building. It is also equipped with the damper. See, this is the bracing, and then this is the damper. So aesthetically we can cover it actually. It will not affect on the architectural appearance of the structure. This is again the building. See, it has this damper. These are the dampers, viscous dampers. This building has the isolation as well as the MR damper, both. Base isolated building with MR damper, hybrid mechanism. See here, these are the damper. So similarly, the photographs which we have seen, they were related to the single, means the separate, or the individual structure, we can say. That building can be, the dampers can be used to connect the two building also. If we have a structure 1, structure 2, so it is also nowadays very recent area of the research. If we have two structure, then two structure can be connected by means of a damper. So whenever there is a seismic excitation, that both the response can be simultaneously controlled by the damper. This right hand side figure is the mathematical uh, this mass, stiffness, damping, all the parameters. Now let us see a few case studies based on our research. This is some building, just a broad case study I have included, not too much theoretical equations I have included over here. uh, we have this, consider this single story building. This is a single story building. It is basically a symmetric building. These two columns are of different size, these two columns are of the different size. So obviously when these two columns are of larger size, the center of stiffness, or we can say the center of rigidity, will move on the right hand side. If we have, we can change the center of damping also, right? That will create a supplemental, means the eccentricity due to damping, and this is we can say the structural eccentricity, which is the difference between center of mass and center of rigidity. As it is a symmetric building, it will have this uy, let us say it is the displacement in y direction, this is the y direction, and there will be some rotational displacement also. Now this building, whenever it is equipped with the linear and non-linear viscous damper, right, then how we can control the displacement? For that, this is just a numerical, or we can say the research study. So this is the viscous damper which just now we have seen earlier. This is the mathematical model of this viscous damper, that it is the stiffness, it is the damping proportional model. So this is the damper, which is having the piston cylinder, this symbol which you have seen in your physics also, CD, that is a damping coefficient which is proportional to the velocity. So governing equation of motion, just now which we have seen in earlier slides also, it is this mu double dot plus cu dot plus ku, plus this component was there, and if you remember, I have written fd there. So that fd just I'm bringing on the right hand side, just to mathematically solve it using some of the numerical methods. So this is f along with the capital lambda. So F is basically the damper force. For this building, for this particular building, it is a single story building but having 2 degree of freedom. So the mass matrix will be of two size, size 2 by 2, m and mr square. This m is related to the degree of freedom uy, and this mr square, it is related to the u theta, right, polar moment of inertia. So m and mr square. C, that is the damping matrix which we are considering, which we have considered, that is the Rayleigh damping, which is the mass and stiffness proportional, A0m plus A1k, where A0 and A1 we have to calculate. We have the stiffness matrix. Basically, obviously it should include the eccentricity effect. Then we have this one more important parameter, that is the frequency ratio. That is the ratio of torsional to the lateral frequency. Then we have used many methods are there. Those who are working in this area must be knowing many methods are there for the solution of the governing equation of motion. We can call it as a time history method, right? Which includes the Newmark beta method, fourth order RK method, right? Just like as that, one of the methods is state space method. So this is the formulation for the state space method, which gives the solution of this particular equation of motion. This is the equation of the damper fd, that is this one. This fd is this. So fd is cd, that is a damping coefficient, which is this one, cd damping coefficient into the velocity. So cd into velocity ratio alpha. Alpha means it is a damper exponent. It may range from 0.2 to 0.2 to 1 for the seismic application with reference to the Sung book. If it is 1, if alpha is 1, that means it is a linear damper. If alpha is other than 1, then it is known as the non-linear damper. For the to derive the effectiveness, we have used this very simple parameter RE. RE means it is the response of the asymmetric, means control system to the uncontrolled building, right? So obviously when RE is less than 1, that means the control system is effective. RE is the response, peak response of control system to the divided by peak response of uncontrolled, right? Control by uncontrolled. So that means when it is less than 1, that means the system is effective. These 4 earthquakes which we have considered for the numerical study. Now based on that, just a few charts, a few figures, few graphs I have included. uh, just see one thing. RE, this, let's say RE for the, refer the left hand side figure. RE for U theta, it is torsional displacement, and these are the lateral displacement. Lateral displacement on the stiff side, UIS, lateral displacement on the flexible side. All the graph, if you see, means these vertical axis RE, horizontal axis there is alpha. Alpha is ranging from point 1 to 1. So irrespective of any value of alpha, all the graphs, if you see, the values are less than 1. See here, less than 1. That means all, for all value of alpha, RE is less than 1 for the structure having the time period 1 second, eccentricity is this, and damping is 20%. That means the dampers are quite effective in reducing the responses. That is the effect of the damping. This three line indicates the different frequency ratio, torsional to lateral frequency, 0.5, 1 and 2. Similarly, you can say, you can see this particular graph also. Again, all the values are less than 1. With the increase in damping, if we increase the damping, this axis is showing the damping. If we increase the damping, the response will reduce. See, if the damping is, let's say, if the damping is this 1.1, right, 10%, then it is response, that factor is 0.4. If it becomes 0.4, then the response become 0.1. So there is a reduction, significant reduction in the response. Similarly, just a figure for the another torsional responses. This is the bar chart of the same story. All the values are less than 1. If you see on the vertical axis, these are the time histories, which will give you clearly the idea. This red dotted line indicates the uncontrolled response, means the structure without this one, any damper. This black is linear damper, and the blue is the non-linear damper. Alpha is 1 in the black line, alpha is 0.35. You can say all, means whether it is a linear damper or non-linear damper, it is effective in comparison to the uncontrolled system, that is shown with the help of the red dotted line. This is the typical characteristic of the force displacement and the force velocity for the viscous damper. F, you can, you know, I am sure you must be knowing that damper, if it is viscous, then F is directly proportional to the velocity, right? So that, this is the idealized linear damper. So if for this study, for this particular building, if we plot the force versus displacement loop, we call it as a hysteresis loop. So hysteresis loops are these. It is between force and velocity, force and displacement, and force and velocity if we plot, then it will be a incline, means a line. That means it is the idealized linear damper, this one. This loop, what is the meaning of this hysteresis loop? If the loop is having higher area, right, that means the more energy or the higher energy dissipation capacity. So this is for the linear damper. Alpha is equal to 1, and for alpha is equal to 0.35, behavior, force, damper force and velocity behavior is linear, damper force and velocity behavior is non-linear. This is obtained through the numerical study for the actual that particular building. Again, the hysteresis characteristic of the different dampers: fluid damper, viscoelastic damper, metallic damper, friction damper. These are the typical characteristics. So as I mentioned earlier also, each and every damper has their standard mathematical model and control algorithm, which we have to fit in to the equation of motion, and it will give us the particular response, and then we can study the uh, effectiveness of the damper. Now just quickly in a 2 minute I'll show you this particular another case study. It is a 4-story building basically, which we have considered for the research purpose. So this is a structure which is having asymmetry to from here, right? Mass proportionality same, mass and stiffness is same, column size etc, but due to the setback there is some asymmetry, and that has been addressed by means of this particular research. We have used number of dampers over here: semi-active MR damper, semi-active viscous damper, semi-active friction, semi-active variable stiffness, and the non-linear damper. And just I'll give you the idea. Yes, this graph will give you the this is the story displacement versus the displacement story versus displacement. It is a 4 story, so displacement. So you can see the black line, it is uncontrolled without damper. This is the displacement. And if you put all the type of damper, whether it is MR damper, variable damper, friction damper, stiffness damper, or non-linear viscous damper, all the dampers are quite effective in reducing the displacement. Let's say this, see, the displacement is 8 centimeter here, and it becomes directly 2.5 centimeter roughly with the help of the damper, like that. Similarly, this is the torsional displacement. These graphs are for the acceleration that can be also easily controlled, right? These time histories are showing the these are based on the actual study. So you can see all the dampers are, this red color indicates the structure without damper, and the black line indicates the structure with different type of the dampers. So all dampers are quite effective in reducing the, whether it is a torsional displacement or lateral displacement or torsional acceleration or lateral acceleration, and ultimately the base shear and base torque. Okay, so this is just to give you the idea. I have not intentionally I have not included too much formulation or mathematics actually. Just um, briefly I have shown you the result. So just last slide, at the end I will show you one very interesting chart actually, which uh, we have to keep in mind, which normally I share whenever I talk with any of the group. 0 to 1 minute, let us say, at this moment, if earthquake comes, uh, at this point of time, what is the positive thing? Nothing positive, but what is negative? There is a panic, right? Immediately, if the earthquake comes at this point of time, from 1 minute to 1 week, events are aftershock. Uh, Obviously, there will be a fear. That is a negative part. The positive good thing is that within a week from the next minute, there will be some rescue and survival. That is a good sign. From 1 week to 1 month, diminishing interest, because aftershock have been over. So the people will start repairing, means short term repairs will be there. But negative side is that, which is our typical human tendency, this allocation or the blame business to the builder, official, designer, etc., etc. From 1 year to the next 10, no event, no positive, no react, no negative. From 1 year to the next 10 year, uh, no event, no positive, negative part is diminishing interest. We are in this phase from, if you count from our Bhuj earthquake. From 10 year to the next time, reluctance to meet cost of seismic provisions, right? No need to design IS1, no need to consider IS 1893, 13920, right? Diminishing interest and reluctance. And the next time, major earthquake, repeat stage 1 to 7. So this is a sad but true fact, and we as a responsible citizen of state and country, actually we have to break this particular chain, right? We should design the structure for the earthquake resistance. So thank you all. Hello. Any questions?
Yes, sir. There are a few questions in the chat box.
Okay, let me see.
So I will, if it is feasible for you, sir, then I'll be taking it one by one.
Yes, sir.
Yes.
I can read and answer actually. No need. It's okay.
Okay, sir.
How to find the response at flexible edge and stiff edge if floor has only 2 degrees of freedom? Yes, see, for the flexible and stiff edge, if the building is asymmetric, if the building is asymmetric on the flexible and stiff edge, first we have to obtain the response at the center of mass actually, and then at center of mass you will have 2 degree, one is lateral, one is torsional. So with the help of lateral and torsional degree of freedom, with the help of lateral and torsional response at the center of mass, you have to use the engineering mechanics principle, and then you have to transfer it at flexible and stiff edge. Just like as stiff edge, it will be let's say if I say u and theta are the responses at center of mass, then on the stiff edge it will be u plus b by 2. B is the dimension of the building, so u plus b by 2 into theta, so that will give you the stiff edge response, and u minus b by 2 into theta will give you the response on the flexible side. So the engineering mechanics, that principle we have to use. Another question I am reading is, which method is used for the seismic response of semi-active control? How to define the algorithm for the same? See, actually the different selective control means various dampers there, they have their own algorithms. Parallel to that, one question is, which are the algorithms for MR damper which is more effective? Let's say if we have a semi-active MR damper, then for semi-active MR damper, different control algorithms are there, floated and proven by the various researchers, like as Bokven model, clipped optimal algorithm, LQR algorithm. So for our structure which is based, that we have to make the we have to use all the algorithm one by one in our structure, whichever is best fitted in our system, that we can adopt for a building. It cannot be generalized that always this will be best. In general, if the specific question is for MR damper, then for in general for MR damper, out of, as I mentioned, LQR, LQG, uh, clipped optimal, passive off, passive on, number of algorithms are there for MR damper. The most effective in general is clipped optimal. Clipped optimal control is the most effective as far as the MR damper is concerned. Otherwise, in general, for the various damper, different algorithms are there. Let's say if it is a semi-active stiffness damper, then uh, uh, switching control law is there, resetting control algorithm is there. So we have to try one by one all for the particular damper, and then we have to select the best, whichever is best for our system. The same thing for the next question also, that which damper will give maximum efficiency. Actually you cannot again generalize it. It varies from structure to structure. Let us say if we have a in general, just a very simple example if I give you, if you have a tall building, right? For the tall building, the main concern is to control the displacement in comparison to the acceleration. If it is a short building, the acceleration is more governing in comparison to the displacement. So if it is a tall structure, or if it is a short structure, let us say, where the acceleration is already controlled, right? And if you provide the, let's say, the stiffness damper, now normally what is the typical characteristic of the stiffness damper is, whenever you provide the stiffness damper, it will add the stiffness to the structure and it will increase the acceleration, right? So that type of judgment we have to make in the while choosing the dampers. Practical, what is the practical meaning of Bokven model? Practical, I didn't get the exact wording. Practical meaning of Bokven model is developed by the Spencer and the Dyke actually. They have used this Bokven model in modeling the MR damper in the clipped optimal control algorithm actually, which is having standard parameters which can generate the damper response in return. Can we avoid ductile detailing if we provide dampers? No. This is additional. Dampers and base isolations are additional features actually. So ductile detailing is compulsory, necessary. how do we incorporate property of dampers in ETABS? In ETABS, actually, at the most you can use the viscous damper and viscoelastic damper, right? Other than that, if you want to use the any of the semi-active damper like MR damper, stiffness damper, semi-active stiffness, semi-active friction, then it is difficult and little impossible to model the MR damper type of the damper in ETABS or any of the software. For that, compulsorily you have to perform the time history or the numerical method, time history analysis using any of the programming language like Fortran or C++ or MATLAB, and then you have to perform the numerical the time history analysis by using the any of the numerical method like fourth order RK method, uh, state space method, Newmark beta method, Wilson theta method, right? It is difficult in ETABS. Simple passive dampers are possible, and that too only this one, friction, viscous and viscoelastic, but semi-active, no, not possible in ETABS. In case of a torsional irregularity in structure, does it become? No, we can change the if it is you can provide the hybrid dampers also, depending on the need. As I mentioned, that which damper we want to, which property or which response we want to control, whether our focus is to control the displacement or our main focus is to target to control the acceleration. Based on that, you can provide the hybrid damper also, means in some floor provide the let's say the viscous damper, in some floor provide the stiffness damper, so that can be done. Okay, Professor Tarak.
Yes, sir. So, actually, I was waiting for a while. Thank you very much, Snehal sir, on behalf of Marwadi Education Foundation as well as Atal Academy AICTE. We are very much thankful that you have spared your time on this knowledge sharing platform, and you have shared your knowledge, and almost all the questions that we have answered. Now, even if any of the doubt that is there with the participants, so if they will communicate, we will contact you in
Sure,
this
sir.
regard.
Sure. Thank
Yeah.
you.
Yeah. So thank you very much, sir. So with your permission, we end this session. Yeah.
Yes. Thank you, sir.
Yeah.
Thank you
Yeah.
to
And
your
all the
department and your institute.
participants, yes, all are requested to join the next session at the due time. So thank you. Thank you all.
Thank you.